Students, let's try to understand the formation of molecular orbital by linear combination of atomic orbitals. So we are going to understand here LCAO, linear combination of atomic orbital, right? So here see student, the formation of molecular orbital can be explained on the basis of linear combination of atomic orbital, keeping in mind that atomic orbital is an electron wave. Orbital is an electron wave. The wave of the two atomic orbital may be in phase or out phase. Suppose psi a and psi b present in the amplitude are also called wave function, okay, of the electron wave of the atomic orbital of the two atom A and B respectively. Then the situation may be represented as follow. Okay, when the two waves are in phase, constructive interference, so they add up, an amplitude of the new wave will be this one. So here you say that is both are there, that they in phase, same side they are starting. Okay, so that is the when the resultant is going, it is increasing, so that is additive or the constructive overlapping is there. And when the two waves are out of the phase, destructive interference, the wave are subtracted from each other, so that amplitude of the new wave is psi is equal to psi a minus psi b. So here is what is there, this is downside going, this is upside going, so it's the resultant is very less one, so psi a minus psi b. Okay, knowing that the probability is given by the square of the amplitude wave, so psi a plus psi b square is equal to psi a square plus psi b square plus 2 psi a plus psi b, and that is what is that is this is there. Okay, and psi a minus psi b square means psi a square plus psi b square minus 2 psi a psi b. So in the addition, overlap of electron, subtractive effect of the electron, this is what the LCAO method is showing. Now you see student, thus by the combination of two atomic orbitals, two new molecular orbitals are formed, one by the additive effect and other by the subtractive effect of the atomic orbital. The molecular orbital formed by the additive effect of atomic orbital are called bonding molecular orbital, and the molecular orbital formed by the subtractive effect of the atomic orbital called antibonding molecular orbital. The probability of finding electron in the bonding molecular orbital increases. Most of the electron density located between the nuclei of the bonded atoms, and hence interacted strongly by the nuclei, whereas it increases in the antibonding molecular orbital. Most of the electron density is located away from the space between the nuclei, and hence the repulsion between the nuclei is high. In fact, there is a nodal plane between the two nuclei of the antibonding molecular orbital, that is a plane where the electron density is 0, as discussed later. So in the figure, okay, so this is the node, crest and trough are the node. Just as atomic orbital represented by SPD, the bonding molecular orbitals are represented by sigma, pi, psi, and corresponding sigma, pi, delta, and corresponding antibonding molecular are represented by sigma star, pi star, and delta star. It may be pointed out that the crest of the electron wave are usually given by plus sign, and the trough is negative sign. Thus, bonding molecular orbital is formed by combination of plus with plus, minus with minus part, and electron wave, whereas the antibonding orbital are formed by overlapping of plus with minus part, plus with minus part. However, those are plus and minus sign have the nothing to do with the electrical charge on the orbital. This simply represent the sign of the wave function. Okay, so this is what is the our answer, student. Okay, let us have a look over this one. It is important to note that compared with the energy of the combining atomic orbital, the energy of the antibonding molecular orbital is raised by amount greater than the amount by which the energy of the bonding molecular orbital is lowered, or the course sum of the energy of the bonding and antibonding molecular orbital remain equal to that of the combining atomic orbital. The reason for the lies in the fact that in the bonding molecular orbital, the electron density in the internuclear region, that is region between the nuclei, is high. As a result, the nuclei is shielded from each other, therefore the repulsion between the nuclei are very small. In the antibonding molecular orbital, the electron density is in the internuclear region is very low. As a result, the nuclei are directly exposed to each other, that is there is a very little shielding. Hence the repulsion between the nuclei are very large, so that antibonding molecular orbital is raised much higher in energy than the bonding molecular orbital is lower in energy. Thus, we conclude that the antibonding orbital is more strongly antibonding than the corresponding bonding orbital is bonding. Hence, strictly speaking, diagrams are not symmetrical. However, for the sake of simplicity, generally symmetrical diagrams are drawn. The lowering of energy delta of the bonding molecular orbital, that the combining atomic orbital, is called stabilization energy, while the increasing energy delta dash of antibonding molecular orbital is called the destabilizing energy. Okay, it means here you see that is the down one is stabilizing energy and up one is the destabilizing energy, right? This is antibonding orbital upside, bonding orbital downside. This is atomic orbital. This is the formation of bonding and antibonding molecular orbital. So this is what, okay. So in the next video we will try to understand the character of the bonding molecular orbital. So thank you so much for watching, friend. If you find this video helpful, please do like and subscribe the channel, and don't forget to comment.